everybody. My name is Xander. I'm from New Mexico State University. I'm here to talk to you today about Titan's atmosphere and some work I've been doing using some public Alma data. So as we just saw in Alex's talk, Titan is a pretty cool place. It's the second largest moon in the solar system overall, and its substantial atmosphere, haze, methane, and other ice clouds, as well as all the surface liquid features, some of which are temporary and some of which are more permanent, and the subsurface ocean finally make it a really interesting place to study for astrobiology, and as part of this kind of new emerging ocean worlds project that NASA has been undertaking. So most of this was discovered, as we just saw, by the Cassini mission, which really blew the door wide open for Titan and also Saturn studies, but we don't really care about Saturn, and Enceladus as well. So Cassini did a lot of great Enceladus studies, so it's just been a wealth of data coming in since 2004 from the Cassini mission. And part of that was the Huygens probe descent, as we also saw. So in January of 2005, Huygens parachuted down into Titan's atmosphere, and as we went through, for the first time, we were able to finally get below this haze layer on Titan, which previously had just been kind of this big orange ball next to Saturn. And we're really able to see all of these really cool surface features. So there's valleys and mountains and dunes similar to those on Earth, fluvial features, and all kinds of stuff. And as you go down through this haze layer, for the first time ever, you're able to find the fabled city of Los Angeles. So if you've never seen a Titan talk before, that's the obligatory joke. Thank you for not stealing it. So anyway, a lot of these products of the chemistry in Titan's atmosphere come from the dissociation of methane and molecular nitrogen. So as we just covered, it's mostly molecular nitrogen, a little bit of methane, and these things get broken down by energetic particles as well as photons in the upper atmosphere and react with ions and other products from Saturn's magnetosphere, as well as Enceladus raining in with a little bit of oxygen to create all kinds of cool stuff. So there are polycyclic aromatic hydrocarbons, or PAHs, that get formed, and these larger particles kind of accumulate in the lower atmosphere, and some condense out and some kind of form into these larger aerosols or haze products. And this is mostly what I'm going to be talking about throughout this talk. And Cassini, particularly in the infrared, was a great way to study this. So a lot of new molecules were detected in the atmosphere. Here, an example of some Cassini composite infrared spectra from the Sears instrument. So both above and below are from Sears at different wave numbers, or if you're into wave numbers, probably not, or if you're into microns. And so there's, kind of ethane and methane bands and acetylene, all kinds of cool hydrocarbons that get clustered here. So it's just a really amazing data set to both discover new molecules and also kind of see how these things change in Titan's atmosphere as we go from different regions, because Cassini has very good latitudinal resolution. So if you're more into the chemistry of this, here's kind of a diagram, and with the advent of Cassini comes a wealth of these photochemical models which are able to try to predict the products of this atmosphere, see how abundant they are, and kind of see how far we can push the rich organic chemistry of Titan's atmosphere. And so on the left is mostly the products of methane chemistry, which are the hydrocarbons, and on the right are the nitriles. And you don't have to get too invested into this, but a few of them I'm going to be talking about today are HCN, methylacetylene, cyanoacetylene, and these were seen by Cassini. Previously in the submillimeter, we had detected acetonitrile or methylacetylene, and I'll be talking about that as well as a few new products that have been detected recently, and these are acrylo and propionitrile. I may also call these vinyl cyanide and ethyl cyanide because kind of just bounce around. I don't know anything about chemistry, so enjoy that. Anyway. These are really cool products, but in the later part of this year, we're actually going to be losing all this coverage from Cassini. And that's going to be really unfortunate. But Cassini is going through this really cool process right now where it goes between the planet and the inner rings, which is somewhere we've never been before with Voyager or anything else. And it's just going to be a fantastic thing. And this is called the grand finale of Cassini, so look out for that. And we can only wish our own finales were as grand. But until then, we can use Alma to study Titan. So Alma is this large radio telescope that's in the Atacama Desert of Chile. You've probably seen this picture already in other slides talking about Alma, so there were some great introductions. This is actually the only photograph of Alma ever taken, which is why you've seen this picture 4 times. That's not true. So Alma actually uses Titan as a calibration object pretty often. So there are other people talking previously about using Alma to study protoplanetary disks and radio jets and galaxies and all kinds of other cool stuff. So often when that happens, Titan is taken as kind of an image switched off from whatever other target you're using to calibrate their flux measurements. Those go through the pipeline, and then the Titan data gets kind of ejected out into the archive where you too can use it if you want to scoop my dissertation project. So it is there for the taking. Don't do that though. So here are some of the data from the Alma telescope. Some of these public data are only like 3-minute long exposures. They're very short, but even within that, we're able to get out these really cool spectra that show tons of interesting stuff. So there's some kind of methylacetylene bands here, and then these were new detections of a couple of molecules. So we have an ethyl cyanide line here. That's not the only one in the data set. There's plenty more ethyl cyanides everywhere in the Alma data, which is exciting. And also there was an intern at Goddard who discovered this vinyl cyanide or acrylonitrile on the wings of this carbon monoxide line here. And so that was kind of hard to find, but there's been a follow-up study about this, and it's definitely confirmed. And these 2 molecules in particular are pretty interesting because they were studied recently as potential molecules which may form structures within Titan's kind of surface liquid features, these eutectics of methane and ethane in very cold temperatures. Turns out that molecules like acrylonitrile may actually be able to form these kind of liposome analogs, but in Titan's cold atmosphere cold surface chemistry. And because these are kind of polar nitrogen molecules, they've been dubbed azotosomes. And I don't really know too much about liposomes and azotosomes and whatever this sunflower thing is, but this is an interesting way to kind of try to tie the atmospheric chemistry of Titan together with any kind of surface processes and look for interesting astrobiologically significant things there. So here are the list of some of the other molecules that have been studied. And we found all of these with either Cassini or Alma as of now, with the exception of a few here. And recently I put in a cycle 5 proposal to target specifically cyanoalanine HC5N, and then also a type of this primary nitrile, which is propylcyanide, which we found in the interstellar medium so far. So fingers crossed for that to come in, and we'll see what we can find. In the meantime, we can take a lot of this Alma data and make these kind of cool maps of stacked flux. And you can see, even with relatively large spatial resolution compared to Titan, so it's not really resolved, you can see these kind of lopsided asymmetries within atmospheric constituents. So there's ethyl cyanide and vinyl cyanide on the top, and then HC3N and methylacetylene here. And of these 3, methylacetylene seems to be concentrated in the north, and the rest of them are concentrated in the south. This is from 2015, when Titan transitions into the northern summer. So basically what's happening here is you're seeing these 3 products are being kind of condensed down on the winter or southern hemisphere of Titan, with the exception of methylacetylene, which seems to be more resilient to photochemical destruction. Its chemical lifetime in the atmosphere is longer. And this is a really interesting thing that we can see just from these maps. What I'd like to do, in addition to trying to find new molecular species, is to try to actually really pull out very distinct, spatially resolved abundances and temperatures of these molecules in the atmosphere, and see if we can measure these variations over time. And with Alma coming online in 2012, we have this kind of little overlap region where we can use Alma data and Cassini data together to see some of the seasonal transitions as Titan goes into its northern summer. So I do this with radiative transfer modeling. The program I use is called the Nonlinear Optimal Estimator for Multivariate Spectral Analysis, or Nemesis. I didn't make up that name, but there it is. So Nemesis allows you to build a model atmosphere of whatever planet you're working on. You can use it for a variety of different things, and construct this kind of temperature, pressure, and abundance diagram, as well as all kinds of other knobs you can get, and make synthetic spectra out. And you're able to compare that to these data in this kind of goodness to fit least chi-squared method that's iterative, and it's very powerful. And with the addition of Cassini measurements, which are super well constrained, particularly those for Huygens, which actually has been there, this allows our models to be fairly robust. And therefore, you can say that any variation in spectra that you find are due to abundance or temperature variations that are pretty minor compared to the Cassini measurements. So what I've been doing is finding data sets that are spatially resolved to Titan, as in the beam size, the resolution element, is smaller than Titan's disk, usually around a third of it. And you can kind of probe these different regions, these kind of, I'll be calling them south, center, and north for the rest of this for lack of a better way of doing it. And this allows you to kind of pull out different measurements and see if you can actually see these variations across Titan's disk. So as an example, here are a bunch of carbon monoxide spectra, and you don't have to look at these too hard because they all look pretty similar, but there's data from 2012, 2014, and 2015 that are all spatially resolved, and the column in the left is the southern, and then center, and then north, and they all look pretty much the same. The cool thing that you can note here is that the data is in black and the models are in red. So particularly for the 2014 and 2015 data, we're doing a very good job of fitting these lines. Chi-square is like 1. And also another thing to note, which is fun, is that the signal noise actually from the 2012 data to the 2014, 2015 data is drastically increased. And that's because the Alma array has basically doubled in size. So Alma is becoming a very powerful tool. And this is really exciting to see. So we know that carbon monoxide is fairly well mixed in Titan's atmosphere. It has about 50 parts per million up and down all the way because it's pretty impervious to photodissociation. And so that allows us to say any variations in these spectra are due to temperature. And so we can pull out these temperature profiles. This is what Titan's atmospheric temperature looks like. Has this mesosphere up here, and then the stratopause down here, stratosphere, and then the tropopause is below, which is, as Alex said previously, mostly where we see kind of the weather effects, right? So these variations look pretty minor on here, and this is not a great way to diagnose these, but if you dig in further, you can actually see that as we go forward in time, Titan's upper atmosphere in the north gets warmer, and this is due just to increased insolation. And in the southern portions of the disk, we actually see the lower atmosphere getting warmer. And again, this is due to this kind of downwelling of the atmosphere near the winter pole. And so Titan has this kind of like large Hadley circulation that kind of circularizes this around. So I'm writing a paper about this right now and other variations comparing these to Cassini, but what may be more interesting to you is some future work where I'll try to pull out a bunch of different chemical abundance profiles. These are pretty preliminary, and I haven't plugged in the temperatures from the previous study, but this is kind of what you would do, would be to use the temperatures that you find in these different regions and then try to extract abundance profiles out of various different molecules. So here we have HC3N and then C3H4 and CH3CN profiles in the north, the center, and the south. And you don't have to study this too hard again, but basically what we're seeing is that there's enhanced abundances of a lot of different molecules in the poles. And that's mostly due to this kind of circular Hadley cell thing going on and downwelling into the poles. And to see different abundance enhancements there is really interesting and feeds into the kind of permanent lake features that are in Titan's poles. So this is exciting. And in summary, you can detect new potentially astrobiologically significant molecules with Alma in Titan's atmosphere. And you can both measure spatial temperature and also abundance variations of these species, and then do that over time and compare these to previous measurements. For reference, the temperatures that I've gotten out so far agree to Cassini-Sears radio, other stuff within 5 Kelvin, so I think that they're pretty robust so far. And with these correct spatial temperatures, you can get abundance things. So with that, I'd like to acknowledge my funding support through NASA JGFP and some additional Alma stuff. And with that, I'd like to give a bonus talk. Damn it. There it is. Okay, so this talk is just 2 slides. Don't get scared. But I was at the PWR this weekend, and I saw a lot of people talking about their proposed projects with this kind of emphasis on this can help support additional spacecraft missions to places. This is a good add-on to the development of spacecraft. And I wanted to talk about that a little bit because I haven't seen a lot of this talked here. And I was part of this really cool project with New Mexico State, which was to build a CubeSat to go aboard the Europa Clipper mission. And this is not actually going to happen. It was a concept study, but they kind of called on a bunch of universities. And I personally felt like it was a great way to get involved in taking your science, making it manageable, making it small, and then saying, this is something I can only do from space. And CubeSats really allowed you to do that. They're small, and they're cheap, and they're modular. So you basically take a bunch of commercial components and put them together, and you can build this kind of like Lego satellite. And some of these may go on future missions. There have been a couple accepted for Mars, which will be the first interplanetary CubeSats, as we call them, Marco. So if you want to know anything more about CubeSats, you can come talk to me later. We can kind of spitball about how you can take your science and really move it into space on a micro scale, which is really exciting. So for reference, our CubeSat that we developed was the Deployable Atmospheric Reconnaissance CubeSat with Sputtering Ion Detector, or Darkseid, and that is my acronym. And so this is what Darkseid does. It has this deployable solar panel array, which folds out into this large drag wall. And essentially, it does a flyby of Europa. And as it does this, with these panels out, it's able to measure atmospheric density because the CubeSat is so small and very light. So if you increase the surface area, you get much more drag measurement out of it with an accelerometer. In addition to that, it has an ion detector, which can detect this kind of magnetospheric interactions with Europa as it does this flyby. So this was really fun. And if you're interested in talking more about CubeSats, I'd be happy to do that. And with that, I will take questions. Thank you.
That was awesome.
Thanks, appreciate it.
So I have a quick question. I'm wondering, it's a little bit tangential to the talk, but do you know of anyone that's actually looking at ocean circulation for the two types of oceans on Titan and the communication between them in terms of circulation?
Do you mean the subsurface ocean, or do you mean the liquid lake features on the top?
The communication between them, has anyone looked at the flux rates or anything like that?
I don't know too much about the subsurface ocean stuff. I think most of it before Cassini was just kind of modeling, and I mean, since then we have no real idea of how to constrain anything observationally, right? So most of the stuff that we have about the subsurface ocean is from Cassini flybys. So yeah, I don't know too much about that. There may have been some modeling of feedback between there. I know there are a lot of unexplained kind of abundances, and you know, how do we get extra methane into the atmosphere? Is there cryovolcanism? Is there outgassing? Other stuff. So I think the subsurface ocean could play into that. Yeah. You have a follow-up?
Could I make a quick plug for your CubeSat program?
Absolutely.
Okay, just really quick for everybody in here. Everybody in here qualifies, and you can actually make an application. There'll be a call for proposals through a program at Goddard Space Flight Center and STMD Space Technology called NIAC, NASA Innovative Advanced Concepts. So if you have an idea, you don't have to go through a PI, you don't have to go through anybody. You can actually apply directly. It's up to $650,000 in grant money for you to develop technologies and ideas. So if you're interested in that, just find me and I'll help you out.
Yeah, do that. Thank you for saying that. That's really cool. CubeSats are a great way to get involved in this, and also it's kind of on the cutting edge. So if you're looking for something to kind of push your CV, check that out.
Cool. We'll take one more question.
All right, great talk. If you go to where you're talking about the abundance variations,
yeah.
So how much of that do you think is complicated by optical depth effects? How optically thick are these species, and how much will that affect being able to pull that back out?
Good question. So as you saw, the CO lines that I'm modeling are super pressure broadened, right? And so basically just because we know the vertical abundance of that means that we can safely say, like, this isn't super degenerate with abundance variations. Fortunately for us, most of these things are actually not very optically thick, and so they're very thin lines, not very broadened, with the exception of hydrogen cyanide. And hydrogen cyanide has proved to be quite formidable in doing this kind of radiative transfer. So I'm worried that some of these little kind of bulges here are due to inaccurate temperatures, and that will be something interesting to see. But yeah, HCM we have to be careful, and everything else I think is actually, the modeling seems to be pretty robust with that. We can talk more about it later if that didn't answer your question though. Thanks.
Cool. With that, let's thank the speaker one more time.
Cheers.